Next level. Next level.
Utsource is a professional electronic component selling website with deliveries all over the world. Components include ICs, modules, RF transistors, etc. You can make order from their app as well. Plus members get 6 to 10% off plus $500 coupon bonus. So here is my new 3D print, a soldering iron stand, which really helps me in my projects. So guys, my induction heating machine is finally complete, and this what you see is a tile, and this is a plastic piece. So tile is like going to insulate the piece that is going to stay in here, and here what you see is a water bottle, and the pump is attached to it. So this pump is going to circulate water through this copper coil to cool it down when this is functioning. Okay, let me show you. And here I have placed a 12 volts UPS battery, and the pump is on, and it is circulating water through the coils. And now you are already familiar with this power supply that I created in one of my previous videos. So this power supply is what I'm going to use to power up my induction heater, and that's the rectifier that I created in the video before the previous one. Although there is one problem, the capacitor that I used is not able to handle the load properly, and this wire got so hot that the soldering got removed on itself. So I'm going to remove this one and replace it with this one. And if I show you the rating, it is 100 volts and 15,000 microfarad and a surge voltage of 125 volts DC, and this one was only 50 volts with 5,000 microfarad. So the capacitor has also been connected. Now it's time to do the test. Okay, so now I'm going to turn on the machine. So the machine is turned on. So here, as you can see, the fans which are cooling down the MOSFETs, and at present there is nothing inside. Plus I have not even started the water circulation because I'm not heating anything. So let's do the no load current measurement. So here you can see the no load current is 5.35 amperes. So here I'm going to measure the voltage, and you can see it is 45.3 volts, which is very good. 48 is the maximum, so we are in range and not too low. So now I'm going to put this wrench inside the coil and let's see if it gets red hot. So here you can see it's red hot. Now there is one problem. The fans are running at a really high speed, and this area that you see, it is open, so the wind from this fan is coming over here and it is cooling down the piece that I am going to heat. So I should place some barrier over here to prevent the wind from moving from here to this point. Mica sheet. So this is the Banggood's app, and this is the piece that we are using right now. Now here, as you can see, it's stating 40 amperes, but in the description, as you can see, they are saying this test the maximum power is close to 1600 watts and the maximum current is 35 amperes. So the heating ring inner diameter is 70 mm, recommended crucible quad suits maximum support of 58 mm crucible. Here you can see, although this driving plate can withstand more than 40 amperes current, but it is recommended that not exceed 48 volts and 35 amperes to prevent accidents and damage. So for this reason, I'm using 35 amperes MCBs. Yeah, here you see, graphite crucibles can also be used to melt metals such as gold, silver, copper, aluminum, etc. And the heating is uniform, fast and convenient. In this test, the maximum power is close to 1600 watts and the maximum current is 35 amperes. So let's test the crucible and see how much current it is drawing. So here I have the graphite crucible. Let's place it inside. At present the machine is off. There should be some space left in between the coil and the crucible. So the first thing is turn on the water supply. So it's on. Now turning on the machine, and we already have the crucible over here. Setting the meter to current measurement mode, DC 600 amperes. Okay, go. So it's on. So here, as you can see, we are doing around 37.5 amperes, which is very good, and it is still not turned off. And now there is no wind coming from here to this point, and it is like heating at a really high speed. So now I'm going to heat this aluminum piece. So here I'm going to do the measurement for the temperature. As you can see that the crucible is almost red hot. Let's measure the temperature. Oh, more than 400 degrees, 535. 600 degrees. Aluminum should melt at any point. It's red hot. Let's turn off the lights here as well. So the MCBs have tripped. You can see that the crucible is so hot. We were just about to melt the aluminum piece. I think the aluminum piece is liquefying. It is very soft right now. We'll turn on the lights. Oh, you can see it's melting. Even though it is turned off, it is still melting. Okay, you see the aluminum is gone to grass. You are very close to achieving the liquid state. I think I'll have to do something about the MCBs. They tripped off when it was just about time. So here, as you can see, I've connected the capacitors in series. So the capacitance is going to reduce from 7100 to around 3500 MFT, and the voltage is going to rise from 40 to 80. Let's try this one. amperes, as you can see, are only 33. So this time the MCB should not go down. So finally we have melted aluminum. Oh, it's liquid. Hi, today I'm going to make a universal motor speed controller. And this what you see is the machine that runs on universal motor. It's a vacuum cleaner, a dead one. So that's the inside view. You see the universal motor? I have to take it out. So here is our high-speed universal motor. And as you can see here, it is 1000 watts. And that's the impeller. Also, if you have an idea where I can use this impeller, let me know in the comment section. This is a 9 volts to 24 volts variable DC supply, and I'm going to test this motor with this supply. So the motor is working. Let's do some oiling. Now it is running pretty good. So let's make our own speed controller. Components needed for this project are MJE13009 power transistor, variable resistor, 100 kilo ohms, and a 35 amperes bridge rectifier. I also plan on using this capacitor for better starting torque for the motor, and we are also going to need a heat sink. I'm going to use this one. It has 6 MOSFET slots, so I can easily mount 4 transistors on it. So that's the max I could do. It's much better than before at least. And all the transistors that you see in the front will be connected in parallel. So guys, here I'm going to use this universal board. Here the green wire represents common positive for collector and black one represents common emitter for negative. So here, as you can see in this video, I'm doing the step-by-step transistor connection. 3 transistors are being used, each 13009, and all the 3 are going to be connected in parallel, meaning base to base, collector to collector, and emitter to emitter. After that, another transistor is used to drive the base of the original 3 transistors, and then to the base and collector of the driving transistor I have connected the variable resistor, and the circuit looks somewhat like this. The output is variable output from 0 volts to 120 volts DC, and input is 120 volts DC. So guys, it's time to connect the rectifier, and here I have already connected the wires to the AC terminals of the rectifier. Now to the remaining 2 terminals, which are DC, these 2 wires will be connected. Done. This is the supply. At present it is turned off. Now it's time to connect the universal motor at the output. So guys, here I'm going to start with the 500 watts sieving machine motor. So let's turn it on. You see it has started running. that's your home supply, and the rectifier that is converting home supply to DC, and after that comes your circuit. And at the output I've also placed this rectifier, as I said before, and that's your motor, although it's 220 volts, but I'm running it at lower voltage, so the RPM is a little low, but still it is running quite good. Let's increase it. Now guys, let's try this vacuum cleaner motor, 1000 watts. Okay. Let's increase the speed. Whoa! Close up for vacuum cleaner motor. Super close up for the vacuum cleaner motor. Turning on the switch, slowly increasing the speed. It has started running. More. More. 'More. Now guys, let's test this circuit on this super big washing machine motor. Okay. Increasing the speed. More. More. 'And guys, you can also use the same device on DC motors. Obviously the voltage rating is different for this motor. I'm going to run it at 50 volts, although it is written 40 volts here. Yeah, no heating at all. Increasing the speed. Fine. More. 50 volts input from an e-bike charger. Now guys, what will happen if I connect this 1 kilo ohm half watt resistor to the output terminals of this speed controller circuit? For input, I'm using the same 50 volts supply from the e-bike charger. Let's connect the multimeter to check the output. Here it's 3.127 volts, and remember that the input is around 59 volts max. Let's reduce it and see how low we can go. You see, as low as 0.5 volts DC. Yeah, 4.1 volts almost. That is best for charging your lithium ion batteries. Let's go for 5.1. This is the voltage at which your mobile phone charges. 6 volts for your 6 volts lead acid battery, usually used in emergency lights. Your rechargeable 9 volt batteries. And again, we can go or increase to as high as we want. So as you can see that this device is just perfect for charging your batteries. Okay, and here as you can see that we are doing full. Pretty good, huh? But what if we don't have an e-bike charger? We can always use our old laptop chargers and charge our 12 volts batteries. Setting it to 14.4 volts. Very smooth increase in voltage. Yeah, we have the exact 14.4 volts. So let's connect it, and the voltage drop is around 12.16, and the battery is charging. With time it will increase and finally reach 14 volts when I will claim it fully charged. Oops, it has auto turned off. So guys, as you can see that it has gained 13.27 volts from 715 to like 740.
In this video, I'm going to make an inverter without a transformer. Now, a few years back, when I completed my BTech in 2014, I had an electronics book in which there was this basic circuit of an inverter in which they used only a high value inductor and a capacitor, and they created switching to create an AC on the output of the circuit. But the only problem is that it is not going to be very powerful, but it is a basic circuit to understand if an inverter can work without a transformer and step it up. So here is the capacitor. This is a 7100 microfarad capacitor with 40 volts DC. It's a DC capacitor. Okay, that's one of it, C1. And this is an inductor. It looks like a transformer, but it is only an inductor. Guys, a transformer has 4 wires, 2 for input and 2 for output, but this has only 2, these 2, which makes it an inductor. Okay, so that's L1. And now the final, the transistor 13009, which is this one. And before proceeding, let's check if this capacitor is working. Okay, so at present it is showing ohms. Let's change it. Diode, resistance, and you see NF, nanofarad. It automatically goes to microfarad. Well, this one is red, so I'm going to go with red being the positive and blue being the negative. So it is showing 8 or around 7 microfarad. Okay, 7 point something, and here as you can see it is 7100 microfarad. So now we can directly start with the connection part. First comes the capacitor that I will stick over here, done. Then comes the inductor. Okay, done. Now as the circuit shows, one terminal of the capacitor will be connected in series with one terminal of the inductor, so we will do that. One terminal of inductor connected to one terminal of capacitor. Now comes the switching device, which is this. Let's connect this to, okay, and done. And guys, now comes the transistor wiring and connection. You see this terminal, the first one, okay, this is base, this is collector, and this is emitter. Okay, so I will use the thinnest possible wire, the very thin wire for the base. Now comes the collector. Let's move it a little away. Yeah, collector is stuck pretty good. And now comes the last one, the emitter. Okay, so the soldering part is done. Now comes the connection part. This wire that you see, it is the collector terminal of this transistor. So this terminal will be connected to the tapping point at which the capacitor and the inductor are connected to each other. Okay, which is this point. So that is done. Okay, now guys, this black terminal that you see, it is the input as well as the output terminal. So let's strip the wire a little to give an extension for the positive supply. So you see here the positive input will be connected. So yeah, now we have the positive and the negative. So guys, first comes the multimeter that we will connect to measure if the voltage is high enough at the output, pointing it towards 750 volts AC. Now I also have to connect a 12 volts DC source to convert it to AC. You see 12 volts, 7 amperes. It's a UPS battery, and truthfully speaking, a really old one. So this red terminal, as I told you, was the negative one, so it will be connected to this negative terminal. Okay, and I have a clip. Yeah, negative has been connected. This is the base wire. This does not need any connection right now, and this is the positive connected to be connected over here. So guys, let's touch this wire and see if it reflects some voltage. As you can see that it does not reflect any voltage because the base wire is open. So we can connect it permanently. It is not going to drain the battery or discharge it. Okay, now we have this open base terminal. So if we connect it to this capacitor terminal, this one, okay, then there should be some voltage. You see the voltage is so high, around 550 volts AC, again 1000 volts. 1100 volts. So you can see that first I'm touching it and then I'm quickly removing it, touching it and then removing it, and you see some voltage reflected. So this is called the switching circuit, and every inverter has an automatic switching circuit. At present I'm doing it with hands, which means manual switching, but for an automatic inverter, automatic switching is needed. So for that I'm going to use this simple trick of DC motor switching. Okay, this toy DC motor. So guys, what you have to do is cut off one of the winding wires of the armature of the DC motor. This is going to create the on-off switching process, an automatic on-off switching process, one of the most basic possible switching. And after doing that, install the armature, the case and the brushes back as before, and connect one of the terminals of the motor to the base terminal of the transistor, and the other terminal will be connected to the positive terminal of the battery. So this is the other terminal of the DC motor connected, and all I have to do is touch it to this terminal. You see at present it is not showing any voltage. Yeah, done. Now all I have to do is connect a 3 volts battery here, and this should start reflecting a very high voltage. So this is my 3.7 volts lithium ion battery. Okay, so let's start the show. One terminal over here. You see it showed high voltage. Okay guys, now I have glued these two motors on this metal platform. I'm trying it the second time, and let's see the voltage. So as you saw that the maximum voltage reached was somewhere around 50 volts AC.